says we're live. Is it working? Is my audio good? It says I'm really loud. Maybe that's better? Yeah. Let's see. This say we're live. Yes. Awesome. Very good. Number theory. So let's start with some basic number theory stuff. One proof that I really remember enjoying was that if 3 divides n squared, then three divides n. Now, if we think about this, we can actually confirm that this is true, because if you have a number that's a square number, then it's a square of all of the factors. So if you have an a times b equals n, then n squared equals a squared times b squared. And if 3 times some number k equals n squared, then 3k equals a squared times b squared. Is this the way I want to do it? Yeah. Is that right? So then we're saying that either A or B, one of them, is 3. Or is a multiple of 3. Excuse me, I'm getting over allergies. Got a cough. So how do we want to do this? So we can do it using the regular statement, or we can prove this using the contrapositive, and I think that's going to be easier. So the if this is our statement, then the contrapositive would be 3 does not divide n implies that 3 does not divide n squared. Is that really easier? I don't remember. If we let n squared, yeah, this is the way we need to do it. So what we're going to do is we're going to prove the contrapositive by contradiction, I think. So let 3 divide n, let 3 not divide n, and assume 3 divides n squared. Nope. Hang on. It's been a while. 3 divides n squared. No. We're going to prove the base statement by contradiction. Let 3 divide n squared and 3 not divide n. By contradiction. So this is the statement we're trying to prove up here, but this is actually a fairly difficult statement to prove. But what we can do is we can say it can't be the other way. If we let 3 divide n squared and 3 not divide n, that will lead to a contradiction. So 3 divides n squared implies that there exists a k. That is the wrong way to write that. There exists a k in the integers. Okay. Don't need to specify that. Such that 3 times k equals n squared. Now we don't get to divide by n. That's not a valid move here because we're dealing with integers. We also can say 3 does not divide n implies there exists an h in z such that 3 times h plus 1 equals n, or 3 times h plus 2 equals n. But if it was plus 3, then we'd be back to another multiple of 3. So we're going to ignore that. Is my resolution good? Yes. Okay. So if we have one of these values for n, we're going to say n squared equals 3h plus 1 squared, which is equal to 3h plus 1 times 3h plus 1 equals 9h squared. Let's write more neatly. 9h squared plus 6h plus 1 for, let's color code here. That's for this one. Green goes there. Blue goes here. So n squared equals 3h plus 2 squared equals 3h plus 2 times 3h plus 2 equals 9h squared plus 12h plus 4. And now you're probably looking at this going, well, now what? This doesn't look like it makes much sense, but it does, because now we can say this is equal to 3 times 3h not quite, 3h times 3h plus 2 plus 1. And this one is equal to 3 times, or 3h times 3h plus 4 plus 4. Well, but this needs to not be a 4. So what I'm actually going to do, skip to there, is factor that 4, or is split that 4 up a little bit. Why is it saying my stream is having issues? It should not be having issues. Not sure. So here's what we're going to do. We'll do 3h times 3h plus 4 plus 3 plus 1, because that 4 just splits into the 3 plus 1. 3h times. But since this is also a 3, we can factor this 3 into it. Plus 1 plus 1 plus 1. Nope. Yeah. Just plus 1. So now we have equals 3h times 3h plus 4. Nope. Plus 5. Plus 1. But we're really interested in getting it in this form. Undo. We want this to all be in the same form. So what we're going to do is we're going to put that h back in. So 3 times 3h squared plus 2h plus 1. And this is going to be 3 times 3h squared plus 5h plus 1. And now we have to say this is an integer. So 3 times h squared is in z because multiplication is closed in the integers, which means an integer times an integer is an integer. By closure of, and I'm going to abbreviate multiplication in z. And so is 2 times h. So both of those are integers by the closure of multiplication in the integers. And then 3h squared plus 2h is in the integers by closure of addition in the integers. So n squared is an integer. Nope. Nope, hang on. So we've now shown that n squared, I'm going to do this in a different color. This is a thought. N squared is equal to 3 times some integer plus 1. So 3 does not divide n squared. If 3 in this case. Now we got to do the same kind of thought process to the other side. So 3h squared is an integer, and 5h is an integer, both by closure of multiplication in the integers, and then 3h squared plus 5h is an integer, again by closure of addition in the integers. So more thought process. N squared equals 3 times sum k plus 2, or plus, it's 1 again. Plus 1. So 3 does not divide n squared in this case. But since that's all of the possible input cases, then all of the possible input cases that satisfy our assumption, let's case 1, case 2, so no matter what our input is, no matter what n is, if 3 does not divide n, 3 does not divide n squared by the contrapositive, this implies that 3 dividing n squared leads to 3 dividing n, which was to be shown. So we have just proven that any square number that has a factor of 3 has a factor that is a multiple of 3. Yeah. Sounds kind of rhetorical, but that basically means that a square number that's divisible by 3 is also divisible by 9. Because if 3 divides n, then 3 will divide n squared, because 3 squared is 9. So, to clarify, side thought, side thought. If 3 divides n, then 3k equals n squared equals 3k squared, which is equal to 9k squared. So if k, so if 3 divides n, then 9 divides n squared, which is an intuitive fact, and it makes sense, but it makes even more sense when you think backward to 3 dividing n squared. I don't know. I just found that to be a very interesting, very cool side note. I don't know why that's a question mark. If 3 does not divide n, that's not a question mark. Let's write neatly, shall we? Be consistent with notation. Well, that's kind of fun. So let's do another one. Let's see. If we do if a times 9, let's not choose a because that looks too similar. B times 9 equals some number whose digits are x, y, then x plus y equals 9 for any b less than 12, because that works for all of the numbers. Let's do 1 less than b less than 12, because that works for everything from 1 to 11. There's an extension of this that's more complicated to prove, but but I'm not doing that one right now. So we know this because this is one of those tricks for the nines multiplication table that they teach in school. If you have b times 9, we have b here. Let's write better. b times 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 times 9 is 9, 2 times 9 is 18, 3 times 9 is 27, 36, 45, 54, 63, 72, 81, and then 90 and 18. Not 18, goodness, what am I thinking? 99. And this is actually not quite a true statement. So let's fix it. some c times 9 and c where c is an element of the integers. So now we're not restricting it to b being between 0 or between 1 and 11. We're just saying it's going to be some multiple of 9. So then x plus y. So that's 0 plus 9 equals 9. That's 1 plus 8 equals 9. 2 plus 7 is 9. 3 plus 6 is 9. 4, 5 is 9. 5 and 4 is 9. 9, 9, 9, 9, 18. Let's go ahead and restrict it to make our lives easier for the sake of this exercise. B1 is less than or equal to B less than 10. Less than or equal to 10. So we're actually going to ignore the case of 11 because the proof gets more complicated if you have to deal with that. So we got to think about what this means. So b times 9 equals x times 10 plus y, right? Because that's what place value is. We've got 10 to the 0, we've got 10 to the 1's place, 10 to the 2's place, and so on. So we have x times 10 plus y equals 9 times b. Now if we do that, b is always an integer. And obviously x and y are also integers. Let's see. Then we have x plus y equals, and we're back to saying this. Equals 9. So let's see. Let's solve this. We'll solve it for y. And substitute in to get this. To get this in terms of x. So y is equal to 9 minus x, which we can do because we're allowing the existence of additive inverses. Basically, we're allowing subtraction to happen. So then we have b times 9 equals x times 10 plus 9 minus x. So now we have b times 9 equals 10x minus x plus 9. Well, now hang on, we can combine these. So we have 9b equals 10 x minus 1. X minus 1? Nope. Got it backwards. X times 10 minus 1 plus 9. So 9b equals 9x, because 10 minus 1 is 9, plus 9. 9b equals 9 times x plus 1. Well, x is an integer because it's a digit of a number, and you can't have 3.1 as a digit in a number. So you can't have 3.15 5. You can have 35, but you can't have 3.15. That just doesn't make sense. Because x is a digit. So x plus 1 is an integer because addition in the integers is closed. So what we've just proven is that assuming both of these things is valid, but we haven't said, we haven't proven the if. So to prove the if, we have to assume one and not the other in this case. So let b times 9 equal x times 10 plus y. This is just to do it, this is to state it formally, where b is in the integers such that 1 is less than or equal to b less than or equal to 10. X and y are both integers such that yeah, 0 is less than or equal to x or y, depending on which one we're talking about, is less than or equal to 9. Right? And this is because we're proving by contradiction. X plus y does not equal 9. Actually, no. We're going to assume that equals 9, and that is not the case. Right? Yeah. So, yeah. Okay, so then we're just going to kind of repeat this process from over here. Use our thinking on paper and put it over here. So we're going to say y equals 9 minus x by the closure of addition and the existence of additive inverses in the integers. then b times 9, that's supposed to say then b times 9 equals, or does not equal, x times 10 plus 9 minus x Can we do it this way? I want to say this is not right. Because does not equal is not a very strong statement. I don't know that you can treat it this way. No. No, you can't do that. So we're going to start there. And then let me look at something real quick. That's not what I'm looking for. We have to start here because we have to end up with a statement of equality and show that it's not true. So, yeah, we'll start with x plus y does not equal 9. Then suppose if it doesn't equal 9, x plus y equals some other number, any number, we'll call it k, with k in the integers. Then y equals k minus x minus x. So b times 9 equals 10x plus k minus x, because we're just substituting this in for y. So then we have 9b equals 10x minus x plus k. 9b equals 10 x times 10 minus 1 plus k. So 9b is equal to 9x plus k, but that means since x is an integer, since x is in Z, and then this is in the form of that divisible thing. That means that k has to equal 0 or k is equal to 9 in order for this relationship to be true. But if k was equal to 0 or 9, in either case, we could condense that down and x would just be increased by 1 or not. X would either stay the same or increase by 1, and it would still be a multiple of 9. K not equal to 0, 9. Yeah. Which contradicts our assumption. Therefore, the assumption namely that x plus y does not equal 9 is false. So b times 9 equaling x times y implies that x plus y is equal to 9 times equal to 9, which was to be shown. I'm debating on whether or not to do the Mandelbrot, because I think that's going to take more than 15 minutes. I think we'll pass on that for today. So if this was helpful at all in helping you kind of think through proofs and understanding what's going on, how to form a valid proof that's mathematically rigorous, hit the like button, subscribe, if you want to see more of this, be sure to comment down below. Tell me what you want to see. Join the Discord. We've got chat rooms there for all kinds of different problems. I check it periodically, so you may catch me in there. Somebody else may be able to help you if I can't, and I may pull from the Discord for problem requests in the future. So be sure to join there, and we'll see you guys next time.